So let's start. Good morning and welcome to this lecture. This is lecture number 12. We are dealing with thermodynamics, I guess. And what was the last thing that we discussed? Anyone remembers it? What we were discussing in the last class? Okay. I think we had done all the processes and we were trying to and we are discussing work done in various processes. We had discussed the adiabatic process. Anyone recollects it, or shall I go back and revise it? Do we remember it? Everyone?
Yes, sir.
Pakkar, sir?
Yes, sir.
No doubts on that now? Okay.
No, sir.
We had discussed cyclic process. We had discussed cyclic process. We need to do one or two more problems on that. So we will do that as well. Let me first begin with, I think we were dealing with the adiabatic process, and we had seen work done in an adiabatic process. Where is that adiabatic process? Yes, we had found out the work done in this process, the adiabatic process. We had seen how we can find out the amount of heat is zero, so work done is negative of change in internal energy, and we had the form. We also had seen the equation of state for adiabatic process in different ways. We had seen it in the form of P V is equal to nRT. We have done it in the form of PV raised to the power gamma is equal to constant. Everyone remembers it? Yes or no?
Yes.
Okay. Now what we can do is we can do the next process. You might not find in books. I think process number 5 or 6. Polytropic process. Polytropic process. Now what is this polytropic process? You can say this polytropic process is probably any sort of a general process. Now any sort of a general process, we can represent it in this form. PV raised to the power eta is constant. Now you may have a lot of process which come in this form. This eta could be anything. This eta could be any number. It could be a positive number. It could be a negative number. It could be an integer. It could be a fraction. It could be anything. But this eta should not be equal to 1, because if eta becomes equal to 1, it becomes which process?
Isothermal process.
Isothermal process. So eta should not be equal to 1. This eta can also be equal to gamma. If this eta becomes equal to gamma, this becomes a which process?
Sir?
If eta becomes equal to gamma, then which process it becomes?
Adiabatic.
Yes, so adiabatic process is also nothing but a polytropic process. All processes can be included in this category if we can represent it in the form of PV raised to the power eta is equal to constant. So that becomes the equation of this polytropic process. PV raised to the power eta is equal to constant. This equation is written in terms of P and V. Similarly, we can write the equation in terms of V and T, and similarly we can write the equations in terms of P and T. It would be exactly same as the equation that we had done for adiabatic process. The only difference is instead of gamma, you will have eta. Do we understand this? Yes or no?
Yes, sir.
Now, if I draw the PV graph for this process, if I draw the PV graph for this process, This PV graph for this process will also look just like an adiabatic process or like an isothermal process. It will be something like this. What will be the slope of this graph? What will be the slope of this PV graph? At any point, if you find out the slope, what would be the slope of this graph at any point? At any point, let me call the volume as V and the pressure as P. Now, from whatever we have studied so far, you must be able to tell me what will be the slope of this PV graph at any point where the velocity, where the volume is V and the pressure is P. What will be the slope? Huh? What will be the slope of PV graph for this polytropic process? Yes.
P by V, sir.
Hmm?
P by V.
Go back. I'll give you 5 minutes. Go back and see and give me the correct answer. This will be a revision. I guess you have probably forgotten how. Go and see the slope of the different graphs and give me the answer then. I'll give you 5 minutes. That will give you a time to revise as well.
Yeah.
See, it is minus eta times P by V. That is the slope of the PV graph for a polytropic process, minus eta times P by V. Do we understand this? The slope of PV graph would be like this. Now, and I don't want to do it in a different screen. Can you tell me what will be the change in internal energy for this type of process? If I do this type of process on any ideal gas, the change in temperature, you can give me the answer in terms of change in temperature or anything else. What will be the change in internal energy for any gas which is undergoing this process? Yes. Next question. It has a very simple answer, not a complicated one. What will be the change in internal energy for any polytropic process? Again, you have forgotten everything. 2 minutes you have. Go
NCV
back.
delta T, sir.
Yes.
NCV delta T.
NCV delta T. That is correct. So you can write it in different ways. You can write it as N R upon gamma minus 1 into delta T. Yes or no? Yes or no?
Yes, sir.
Sir, why it is gamma?
I don't know. You
Why
don't know?
not eta? Why not eta, sir?
You don't know? I'll give you 5 minutes. Think about it and tell me why it is gamma, not eta. How did you get it?
CV is R by gamma minus 1.
Change in internal energy is same for whatever process. So you have to keep on revising it. Okay. Now I can write in a different way. N into R into delta T can be written as P2 V2 minus P1 V1 divided by gamma minus 1. Yes or no? Yes or no?
Yes.
Yes
Yes, sir.
or no?
Yes, sir.
Next question is what you have to tell me. What will be the work done in this process? Go back, see, and tell me what will be the work done in this process. I'll give you 2 minutes. You look at this process. This is the equation of this process. Does it look similar? Does it look familiar? Does this equation look familiar? Does this equation look familiar?
Yes, sir.
To what?
Adiabatic process.
Do you remember what was work done in adiabatic process?
So minus delta U.
Take a deep breath. Think again. Deep breath. Go back. Take a deep breath. Deep breath. The deepest breath in the entire universe, and take it. And then give me the answer. What is the work done in this process? What was the work done in adiabatic process? Deep breath. Deepest breath possible. We have done so many questions on that also. So take a deep breath. Deep breath. Deepest breath in the entire universe. And then give me the answer. And you know the answer. Take a deep breath. Deep breath, deep. And again, repeat the question. What was work done in adiabatic process? You had given me the formula of delta U. And I accept that formula. That is correct. Similarly, I'm asking you, what was work done in an adiabatic process? If you don't remember it, there are ways to remember it. You know the ways to remember it. You have to tell me the formula, and then you have to apply common sense and give me the formula for this. That's all. It is not anything which is hard. It's a very simple, straightforward thing. Yes. I again ask you the same question. What was work done in an adiabatic process? And the answer to this simple question is, sir, work done in an adiabatic process was. Sir, work done in adiabatic process was. Sir, work done in adiabatic process was. Sir, work done in adiabatic process was what? N R delta T upon 1 minus gamma. Here it becomes eta. NR delta T upon 1 minus gamma. That was the work done in adiabatic process. The only difference here is instead of gamma, eta has come. Therefore, instead of gamma, eta will come. You can also write it like this. P2 V2 minus P1 V1 upon 1 minus eta. So if you understand polytropic process, you understand adiabatic process or vice versa. Delta U plus delta W will give me delta Q. So once you know the value of delta U and delta W, you can calculate the value of delta Q. For this process, you can write delta Q as N C delta T, where this C becomes the molar heat capacity for this process. That will be equal to N CV delta T plus NCV delta T plus NR delta T upon 1 minus eta dang danang 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 danang. So C for this process can be written in variety of forms. It can be written in this form. Or it could be written in this form. Do we understand this, or this has gone above that saying bye bye? I'm going, bye bye. I'm going. Pongal ke sath I'm going. Makar Sankranti ke sath I'm going. I'm gone with the kite. I've been cut and I'm gone. Gone? Above our heads? Eh?
No, sir.
Pakka na, sir?
Yes, sir.
Thank God, sir. You have 2 minutes, sir, to understand this process, sir. What they are going to ask in this question? They are going to ask what is the change in internal energy. They are going to ask what is the work done. They are going to ask what is the heat supplied, and they are going to ask what is the C, molar heat capacity for this process. If you remember, I told you that molar heat capacity for different processes are different. Have you noted it down?
Yes, sir.
Huh?
Yes, sir.
Then you have a question, my dear friends. Question coming up for you. A gas undergoes a process. PV square is equal to constant 2 moles of a diatomic gas undergoes this process. The change in temperature is delta T, which is 50 degrees. Find everything. What do you mean by everything? Delta U, delta W, delta Q, and the legendary C. You have 2 minutes to give me the answer, else I shall do the needful. Okay, so I have some answers. Let's see. Yes. Delta U. How did you get delta U?
250 R, sir. That
How
is
did you get it?
NCV delta T.
N is 2. How much is CV for this gas? For this gas?
5 by 2 R.
Into delta T is 50. Congratulations, your first answer is correct. It is 250 R. Dan, dan, dan. Then work
Sir,
done in this process.
minus 100 R. It is
Minus 100 R.
N
How did you
into
get
R
N?
by 1 minus eta into T delta theta.
N into R is R into delta theta is 50 divided by 1 minus 2. And the answer is minus
Minus
100. Delta Q.
minus 150 R, sir.
You can just add these two and you will get 150 R. Then to get the value of C, you can do it in 10,000 different ways. You have got delta Q, so you can divide delta Q by N into R. N is 2. Do you understand this?
Yes, sir.
So you can do it in this way also. You could have done it by the original formula also. Let me do it here. 2 into 50. So from this also you can get
3 by 2 R.
3/2R, that is the specific heat for this process. Do we understand this, or this has gone above our head saying bye bye, bye bye, bye bye, bye bye, bye bye? Okay. That takes me to the next question, my dear friends. Question number 2 or 3 or whatever. A gas undergoes a process where V into T square is a constant. 2 moles of a monatomic gas now. Delta T is given as 50. Let me not change that. Again, you have to tell me everything. What is everything? Everything. 2 minutes to show your talents, else I'll have to show mine. So I have the answers. Delta U is how much? N is 2. 3/2R into delta T is 50. So that is absolutely correct. It is 150R. Okay. What about the next one?
Delta W is minus 200 R, sir.
How did you get it?
Sir, I have square rooted on both sides so that I will get in the form T V power 1 minus eta equals to
Okay.
constant.
You can do it in that way. Or what I do normally, is convert this in the form of PV raised to the power gamma. So how do I convert this in the form of PV raised to the power gamma? You could have done that way also. So I would put T as PV by NR. N and R are constant. So don't have to worry about that. So I can write this equation as V into P square V square is equal to constant. Do we understand this? PV
Yes,
is
sir.
equal to nRT. So T is PV by nR square. N and R are constant, so don't worry about that. So I can write this equation now as P square V cube as constant. Yes or no?
Yes, sir.
Or I can write this as P into V raised to the power 3/2 is constant. Do we understand this?
Yes, sir.
So basically what it gives me is it gives me the value of eta from this way. The value of eta becomes 3/2.
3/2.
You could have done it this way, or you could convert it in the form of Vt raised to the power whatever that. I don't remember that formula. I only remember PV raised to the power gamma, so I always do it this way. You could have done it anyway. Anyways, the bottom line is you have to get the value of eta. Once you get the value of eta, then the process is very simple because del W work done is NR delta theta. N is 2, R is R, delta theta is 50 divided by 1 minus eta. 1 minus 3/2, and the answer is
Minus 200 R.
minus 200 R. Minus 200 R. So delta Q becomes
Minus 50 R.
minus 50 R. And C becomes
This is the biggest doubt. Sir, here I have a doubt. C can be negative, sir?
I mean, if you are getting negative, this and again I've created a hypothetical process in which the change in internal energy is less and the work done on the gas is more. So it's coming, I can't help it. Work is done on the gas and the change in internal energy is more. So if C is coming negative, I will have to take that. So what is the value of C coming?
minus R by 2, sir.
Minus R by 2. That means when you increase the temperature, heat is actually coming in, right? No, heat is going out. Why it is going out? Because more amount of work is done and the internal energy is not changing that much. It's an hypothetical process that I have created. Anything can happen in a hypothetical process. Do we understand this?
Yes, sir.
So if any question comes in this category, you should be able to solve it and see how that process can be done. Do we understand this?
Yes, sir.
Now comes the next question. And let's see how good we are in understanding what we have understood. PV graphs. I'm going to draw PV graph of certain processes. The first PV graph is like this, graph number 1. The second PV graph is like this. The third PV graph is like this. The fourth like this. I'll have to probably just give me a minute. Let me draw it. The third one here. Fourth one. Fifth one. Sixth one. And the seventh one. I've drawn 7 different processes. And here it's a match the following question. So here there are the different processes given. The first process is given as isochoric. Second one is given as isobaric. All are expansion processes. Third is given as isotherm. D is adiabatic. E is PV raised to the power 1 by 3 is constant. F PV square is equal to constant. G n 2 3 4 5 6 7. G is PV raised to the power minus 3 is constant. This is a process drawn for a monoatomic gas. You have to match and tell me which process is which. And I'll give you the 7 processes A, B, C, D, E, F, G here and 7 processes here. And I can assume that one process is going to match one graph. You have 2 minutes to give me the answer for this one. Yes, tell me. The first one is an isochoric process, the easiest one.
It's 7, sir.
It has to be 7, so I will write this as 7. Yes.
Isobaric is 2.
Isobaric. Dung 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 dung. It is also very easy. This is the isobaric process. Correct. This is number 2. Now comes all these.
Isothermal is 3, sir.
You have to take deep breaths and then you will get your answer. The easiest one after this, from where I see, would be this process G
It's 1, sir.
is 1. That is 1 because this is the only graph which has a positive slope.
Positive slope.
So that is the only graph which has a positive slope. So this has to be 3. Now, no, sorry, that has to be 1. Now you have to look at all the processes, and what you do, you write all this process. This is PV is equal to constant. This is PV raised to the power 3 by 2 is constant. Now you look at the process which has got the maximum or the minimum slope, negative slope. The maximum slope is F. Do we see this? Yes or no? No, yes.
Yes, sir.
Now the answer becomes simple. Which is F?
6, sir.
6 is F. Do we understand this, or this is going above our heads saying bye bye?
Understood, sir.
Then you look at the next higher number. Which slope is less than this?
3 by 2, sir.
3 by 2, sir. That is correct, sir. So that is your next 3 by 2 process, adiabatic. That is number 5. Do we understand this, or this is going above our head saying bye bye?
Understood, sir.
Now you look at the next higher process. Next process which has the slope which is less than this.
Isothermal, sir.
Then it is isothermal, my dear friend. Then this is isothermal, my dear friend. Then this is isothermal, my dear friend. So isothermal has to be number 4. And whatever is left is between 0 slope and 1. That has to be 1 by 3. So that is your last one. PV raised to the power 1 by 3. I could have created one more here. I could have created one more here. Between 0 and 1, we have 1 by 3. Between 1 and 1.5, I did not have any process. So I could have created a process. PV raised to the power 0.7 is constant. That process would have come between 4 and 5. Do we understand this?
Yes, sir.
No, sorry. That process will come between, 0.7 will come between 0 and 1. 1 and 1.5, if I create a process, PV raised to the power 1.3 is constant. That will come between 4 and 5. Do we get this?
Yes.
So basically, this is how you need to find out all these processes. Once you understand their significance, you should be able to deal with their graphs and their slopes. You just have to look at their slopes and nothing else, my dear friends. Do we understand this? Yes or no? No or yes? Huh?
Yes, sir.
So just look at the process and we are done. The next process, we have already seen it, but we will again have a look and see a couple of examples on that. It's a cyclic process. Cyclic process. So you can write the next heading, cyclic process. Cyclic process. Now the cyclic process may not be a single process. This will be a series of process. You will start from one point and you will end on the same point. Do we understand this? Yes or no?
Yes, sir.
Now for a cyclic process, delta U is equal to 0. Do we understand this? Yes or no?
Yes.
Huh? Then delta Q will be equal to delta W. Now this equation that we have written, this equation that we have written is for the entire process. Do we understand entire cycle? For the entire cycle, this process, this equation is valid. That means net heat in the entire cycle is equal to net work. Net heat for a cyclic process is equal to net work. Do we understand this? Yes or no? No, yes. We understand this.
Yes, sir.
Now, when we talk about work, it is again, you must remember that if this is a clockwise cycle, the work done would be positive, and if it is an anti-clockwise cycle, the work done would be negative. Do we understand this? Yes or no? No, yes.
Understood, sir.
If it is a clockwise cycle, it has to be positive work, and work is the area in between the graph. Yes or no? No, yes.
Yes.
If it is a clockwise cycle, then it is positive work. If it is anti-clockwise cycle, if it is negative work. Yes or no? No, yes. Now, most of the questions that are going to come in a JEE will be on this cyclic process. The most difficult ones can be asking you the efficiency of the cycle. Efficiency of the cycle. These are the most difficult ones, and they might require a lot of calculation. So be very careful. When we talk about the efficiency of a cycle, then this is the total work done, net work, divided by not the net heat, because net heat is net work are 0, divided by the heat absorbed. Heat absorbed. Do we understand what I'm saying? Heat absorbed in the cycle. Positive heat. Heat inflow into the cycle. Do we understand this? Do we understand this? Now, for any heat engine, you can write this as in this formula, this basis. For any heat engine, you can write eta is 1 minus Q2 by Q1. What is Q2? What is Q1? What is Q2? What is Q1? Q2.
Heat in the
Q2 is the heat Q2 is the heat rejected Q1 is the heat input. Do we understand? Now heat rejected would be negative. We will not use the negative sign here. We will use the positive sign. Heat input will be positive, so you can use it in the same way. Now for any given heat engine, you have got a cycle which is known as the Carnot cycle. Now this Carnot engine or Carnot cycle is an ideal cycle, which we will see. This is an ideal cycle, and this gives the maximum possible efficiency of a heat engine which is working between two temperatures. So this basically eta 1 minus T2 by T1 is the maximum possible efficiency for a heat engine, and that is only possible for a Carnot engine. And this Carnot engine or Carnot cycle is a theoretical cycle that does not exist. Do we understand this? Yes or no? No or yes? Everyone has got this, what I meant to say. Have we noted it down, bacha?
Yes.
Okay, there is one question which is a sort of a long question that we can do here just to understand how we can find. Remember, the question that is going to come for this case would be somewhat lengthy, and this is the question that we are going to do, just one question, and that would be good enough for us to understand this concept. This is the question. N moles of a diatomic gas and undergone a cyclic process ABC as shown in the figure. Temperature at point A is T naught. Pressure and volumes are already given, so you can calculate the other temperatures. This is the series of questions, and I'll give you 2 minutes to attempt these questions. You have 2 minutes to give me the answer. The time starts now. Okay. What we got to do? The first thing we got to find out is to find out volume at C. How can I find out the volume at point C? There are different ways, many ways to find out volume at point C. What ways can you think of? What ways you can think of? You can look at the geometry. You can look at the geometry. You can look at this triangle, the pink triangle. I cannot draw it correctly. You can look at this triangle, the red triangle. And you can look at this blue triangle. They are similar, yes or no? Straight line, that's why it's drawn as a straight line. So from similar triangles, you can find out the volume at point C. Do we see similar triangles? Yes or no?
Yes, sir.
This triangle is also similar. All these are similar triangles. Yes or no?
Yes.
Do we see similar triangles?
Yes, sir.
So you can write P naught divided by V naught will be equal to 2 P naught divided by V. Yes or no?
Yes, sir.
2 2 P naught divided by V will be equal to P naught divided by V naught. From there you can get V is will be equal to 2V naught. Yes or no?
Yes, sir.
Yes or no?
Yes.
Now once you know this, at which point do you think the temperature is maximum? Here the temperature at point A. Temperature at point A is given as T naught. From there you can calculate the temperature at point B. Yes or no? It's an isochoric process. Yes or no? Temperature at point B will be 2 times of T naught. Once you know the temperature at point B, you can calculate the temperature at point C, which will be equal to 4 times T naught. Yes or no? After that, pressure and volume both are decreasing, so temperature will decrease. So the maximum temperature will be at point C. That will be equal to 4 times T naught. Do we understand this?
Yes, sir.
Do we understand this? Yes or no?
Yes, sir.
So the maximum temperature is 4 T naught. The third question is, what is the total heat given to the gas? Net heat. He is talking about net heat. How do you find out net heat? Delta Q net will be equal to delta W net. Yes or no? No or yes?
Yes, sir.
That is nothing but the area under the graph. Yes or no?
Yes.
How much is the area under that graph? It is half P naught into V naught. Yes or no?
Yes, sir.
Now we just have to find out in which process heat is given out and in which process heat is given in. From A to B, temperature is increasing. Delta U is positive. Work is not done, so delta Q is positive. In B to C, you can find out the positive heat. The heat which is given positive. Positive heat or heat given delta Q positive or heat input. Only in two process heat is input. Heat is input in the process A to B and heat is input in the process B to C. Do we understand this?
Yes, sir.
A to B is an isochoric process, NCV delta T. B to C is an isochoric process. A to B is an isochoric process. You can find out the heat given, yes or no. N is N. CV. CV is 3 by 2R into delta T. Change in temperature is T naught. Yes or no? No or yes?
Yes, sir.
Plus from B to C is an isobaric process. Heat given is N C P delta T is diatomic gas. I've written 3/2R. It should be 5/2R. Five by 2R N into 7/2R into T naught. So how much is this coming?
19 NR T naught by 2.
Huh?
Sir, from B to C it is 2 T naught, no sir. Temperature change.
Oh, sorry. Yes. It is 2 T naught. Sorry. I made a mistake. So how much it is coming? 19/2. Yes or no?
Yes, sir.
That is the heat injected. Now you can find out the efficiency. You have to find out the heat rejected. How will you find out the heat rejected? You know the heat injected is 19/2. So you can find out the heat rejected. Yes or no?
Yes, sir.
Total heat is given. So heat injected minus total heat will give you heat rejected. Yes or no?
Yes, sir.
Yes or no? So heat output, if I write it, so this will be 19/2. Total heat minus net heat. 19/2 minus half. It will be minus 9 RT naught. Do we understand this?
Yes.
Efficiency of the cycle is net work upon heat in into 100%. So that is half P naught V naught divided by 19/2. R T naught can be written as P naught into V naught. Yes or no? Into 100%. So your answer would be 100 by 19%. Do we understand how I've done this? Yes, sir, or no, sir?
Yes.
Everyone understood this?
Yes, sir.
Pakka? I'll give you 2 minutes to note this down. The next heading that we are going to write is known as the Carnot engine or the Carnot cycle. This Carnot engine or the Carnot cycle is an ideal cycle which obviously is not possible. So this is an ideal cycle which is not possible. In this ideal cycle, you will have 4 processes. You can see A to B. A to B is an isothermal expansion. B to C is an adiabatic expansion. C to D is a isothermal compression, and D to A is a adiabatic. It's an adiabatic compression. So basically this cycle is a reversible cycle. It's an ideal cycle in which is operating between two temperatures. One is known as the temperature of the source. This is the source. It works between two temperatures, T1, which is known as the temperature of the source, where heat is given in to the system. Then there is one which is known as the sink. T2 is the temperature of the sink from where heat is given out. Heat giving in or given out is an isothermal process. This is an ideal cycle. The efficiency of this Carnot cycle, is maximum, and that is 1 minus T2 by T1. What is T2? What is T1? What is T2? What is T1? There are only two processes in which heat is given in or given out. Heat is taken in the process A to B. Heat is given out in the process C to D. So 1 minus Q2 by Q1. And this 1 minus Q2 by Q1 for this cycle is equal to 1 minus T2 by T1. And therefore, the efficiency of a Carnot engine or a Carnot cycle is maximum. The efficiency of a Carnot engine or a Carnot cycle is maximum. Do we understand this Carnot engine or Carnot cycle?
Yes, sir.
I'll give you 2 minutes to note it down. The next heading that we are going to write and understand is a heat engine. First, listen to me, and then you can understand. Heat engine is any engine that you use. The engine that is in your car, the engine that is in your bike is your heat engine. Now, what happens in a heat engine? You are taking heat. You are taking heat from a hot reservoir which is at a temperature T1. Now, in the engine, how you are getting this heat? You are getting this heat by burning fuel. So that is your heat source. Do we understand this?
Yes, sir.
Now, because of that heat, what happens? Your piston of the engine moves up and down, and that is what that rotates your wheel. Yes or no? That is your work output that you are getting. Do we understand this?
Yes, sir.
Then you are rejecting exhaust gases outside. That is your heat rejected out. That is known as your sink. Do we understand this?
Yes, sir.
That is known as your sink. You reject the heat to a sink, and you have a working substance. This working substance is your gas or fuel which you are employing. So basically, this heat engine consists of three main parts. One is source at a temperature T1. One is reservoir or sink at temperature T2, and the third one is a working substance. The third one is a working substance, that is your gas which is working. Efficiency of a heat engine or efficiency of anything would be output, which is work done, divided by input, which is Q1. Yes or no? So you can write
Yes,
this
sir.
eta as W divided by Q1, but W will be equal to Q1 minus Q2 divided by Q1. From here, you can get 1 minus Q2 by Q1. Do we understand this?
Yes, sir.
Now, if this heat engine works on Carnot cycle, it will have maximum efficiency. What will be the maximum efficiency for this heat engine? For this, it has to work on a Carnot cycle, and the maximum efficiency will be 1 minus T2 by T1. Do we understand this?
Yes, sir.
This 1 minus T2 by T1 will always be greater than 1 minus Q2 by Q1. In case of a Carnot engine, it becomes equal to 1 minus Q2 by Q1. Do we understand this?
Yes, sir.
This, my dear friends, is what we call as a heat engine, and you just have to remember Q1, Q2, T1, T2, source, heat source, sink, and the efficiency. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Then the reverse of the heat engine is your refrigerator. Sometimes it is known as your heat pump. It is pumping out heat. Your refrigerator or your AC, it works on the same principle. Heat pump. So what does the heat pump do? It takes heat from a cold reservoir. It takes heat from a cold reservoir T2, some amount of work or electricity it is going to consume. Do we understand this? So work is input, and then it is going to give out heat to the hot surroundings. Do we understand this? Every refrigerator has a coefficient of performance which is same like efficiency. Coefficient of performance, what it is performing? The performance that it is giving is the heat which it is extracting from your inside, and what is the input that we are giving? The input is the work done. So in this case, your efficiency becomes Q2W by Q2 by W. Do we understand this? Yes or no?
Yes.
If you put it in the formula, it becomes Q2 upon Q1 minus Q2, or it becomes 1 by Q1 minus Q2 minus 1. If it is a Carnot refrigerator, Q1 by Q2, remember, will be T1 by T2, and then you can have this formula, which is the maximum possible coefficient of performance. Do we understand this? Yes or no? Or it has gone above our head saying bye bye, bye bye, bye bye. You'll have 2 minutes to note this down. Then let us move ahead and solve one question. This is the question. I'll give you 2 minutes. Whenever they say that the refrigerator cycle is reversible, we'll assume that it is working on Carnot cycle. Do we understand this? The temperature inside and outside is for 260 and 300 Kelvin. Assume that the refrigerator cycle is reversible. Calculate the heat delivered to the surroundings. I'll give you a minute to do this.
So 52 by 11.
So how are we supposed to do this? We just have to find the coefficient of performance beta. Yes or no? Q2 heat taken out divided by work done, which is nothing but T2 upon T1 minus T2. Yes or no?
Yes.
T2 is 260 divided by 315 minus 260. Yes or no? Yes or no?
Yes, sir.
So how much we are getting from here?
52 by 11.
52 by 11 is equal to Q2 divided by W. Heat delivered to the surrounding, that means you have to find out Q2. Every 1 joule of work, so work is 1 joule, so Q2 becomes 52 by 11. Everyone understand this? Yes or no?
Yes, sir.
Okay, we can do one more question on heat engine. Do it fast. I have to give you 2 more definitions before the end of the class today. So this is the next question. A Carnot engine working between 400 Kelvin and 800 Kelvin has a work output of 1200 joules per cycle. What is the amount of heat supplied? I'll give you a minute. Do it fast. So what we got to do is simply find out the efficiency eta. Efficiency eta is work done divided by Q1, and that is equal to T1 minus T2 divided by T1. Yes or no?
Yes, sir.
So from there you can find out eta. Uh, Q1 is has a work output is given. So from there you can find out the eta, I think, is coming as 0.5. Yes or no?
Yes, sir.
So from there you can find out the heat input will be 2400 joules. We understand this? Yes or no?
Yes, sir.
That takes us to the next thing, which is the second law of thermodynamics. We just have to read the statement. Second law of thermodynamics. What is the second law of thermodynamics? We can express it in terms of two statements. One is known as the Clausius statement. The Clausius statement tells us that it is impossible for a self-acting machine to transfer heat from a colder body to a hotter one without the aid of an external agency. It basically tells us that heat can only flow from hotter body to a colder body. Yes or no?
Yes, sir.
And to make it flow from a colder to hotter body, you need to do some work. So that means it is basically telling us for a heat pump, your work done cannot be equal to zero, or the efficiency of beta cannot be equal to infinity. Do we the coefficient of performance cannot be equal to infinity. Do we understand this?
Yes, sir.
Now, the reverse of this is known as the Kelvin-Planck statement. This Kelvin-Planck statement is about an heat engine. Now, you cannot devise a heat engine that can convert entire heat into entire work. Do you understand this? Some amount of heat would have to be given out from that heat engine. That is the Kelvin-Planck statement for the second law of thermodynamics. So you have written the Clausius statement.
Done, sir.
Then comes the Kelvin Kelvin-Planck statement. It basically tells us that for a heat engine, your Q2 cannot be equal to 0, or your efficiency of a heat engine cannot be equal to 100%. That means there would be some amount of heat which would have to be given out to the surroundings. You cannot take heat from a reservoir and completely convert into work. Do we understand this? So basically, second law of thermodynamics tells us in which direction heat flows. It only flows from where to where?
High to low.
In which direction heat flows. Or second law of thermodynamics tells us which process is possible and which process is impossible. Do we understand this?
Yes, sir.
So this brings us to an end of this epic topic, thermodynamics. We have dealt with everything in thermodynamics. In the next class, what we are trying to do, we will be moving on to heat transfer quickly and fast, and we'll try to cover it up in 2 or 3 classes as possible. Everyone has understood what we have done?
Yes, sir.
You have noted down this one?
1 minute.
Okay, note this down. Let me know. From my side, the class is over. I'll see you in the next class tomorrow, and we'll move on with heat transfer. Take care and God bless you all.
Sir, is